Great, thanks very much, everyone, for I guess staying in the afternoon. So this is going to be very different from I guess the talk that you had. I guess as build, right? This is a kind of industry piece, and yeah, I guess I intentionally took some direction from the kind of Stephen Hawking popular science approach, and I haven't got any equations in my presentation. So hopefully it's a different cadence from the presentation you just had. So I'm Shane. I'm Director of Element Energy. So we're a consultancy, and we focus on trying to solve problems in the low carbon sector, which is almost intractable. I guess pretty hard. Sometimes one feels somewhat in despair that things are moving very, very slowly. But we focus on low carbon systems and trying to solve some of the problems there. So I work in our smart energy systems team. So I guess what that means is that all of the areas that we work in, we're able to kind of pull all of that together, and we try to take a kind of a whole systems approach to solving decarbonisation challenges in the energy sector. And they tend to be kind of longer term, so we're looking at longer term issues out to 2050 and how do we decarbonise, and they're multi-vectors, so transport, heat and power as well. And I'm going to talk to you, most of the talk today is about one of the projects that we've worked on fairly recently. So there's three, I guess, sections to the talk. I guess I wanted to just spend 2 slides really talking through a little bit about what's happening with storage now. It's really exciting to finally, I've been working in decarbonisation for 20 years, and there's not very many sectors that have been kind of sustainable, that you can really see things like the train leaving the station. Stuff is really happening, and it's kind of not stoppable. And storage is like one of those things now, and that's really nice to see. But it's a very, very challenging environment for storage still. I'm just going to talk about the UK. Most of the talk. So that's kind of now, and then most of the talk is going to be for like 2050, looking at the long term, what the role of storage is in a decarbonised power system. As I said, that's coming out of some work that we did recently. And then I'll end with some insights, I guess, from that work about how do we get from here to there, because where we are now in terms of our power system and what it would need to look like in 2050 is going to be very different. So so this is not Photoshop. You can go to East London and have a look at this. It's pretty cool. It's called "A Bullet from a Shooting Star" by Alex Chinnick, and I think it's a good metaphor for what's really happening. I mean, it's not just batteries and storage that are causing things to be done differently. It's just data capture from demand-side response assets. Everything is being managed and turned upside down. Everything is being managed differently, and this is a real challenge. Sometimes you can have a technology that just performs a little bit better from the old technology, and that's fine. But then something like batteries, they provide in certain cases such a kind of distinctive advantage relative to the incumbent providers, like for something like frequency response. I'll talk a bit about that in a second. That you have to kind of completely change the rule book in order to accommodate these technologies and even reward them properly for what they're doing, because they're just responding so quickly. So everything is really changing, and that's good, but that's also a problem for batteries. So I guess trying to explain all of the various services that are on the grid is I guess outside the scope. But essentially, there's a range of services that are required in order to keep energy balanced over different timescales. Okay, and that you can look, I guess, to the right-hand side here. There used to be a lot of excitement. So frequency regulation, so balancing the grid in sub-second, making sure the frequency is within certain parameters and doesn't deviate too far. That was, that's a very high specific value, or has been a very high specific value service. And as a result of that, there were lots of new technologies, new entrants. It wasn't just batteries. There was lots of people thinking about charging cars up in the right way that were really going after frequency regulation services. The markets are very small, and we found that, or what we've observed in the UK, where you have open competition for markets, that actually the specific value of the services has gone down enormously, and that's been really surprising to a lot of people who've been working on this for a long time. But essentially, you kind of progress, up the left-hand side here. So that as you go to larger and larger markets, you get to eventually kind of trading or arbitrage. And I guess this is ultimately, if we're talking about 2050, this is where we kind of want to be. We want to be moving energy around, at least over a day, maybe even more. And the market is very, very big, but the value is pretty small, so that's still pretty challenging to make that work. So if you look at what that means in practice, so on the left-hand side, there's a kind of annual report that comes out from one of the industry bodies for storage in the UK, and these percentages, various people that are putting battery projects together, they've been asked, well, what revenue streams are you reliant on for your battery project? And quite a few said frequency response to these kind of fast-acting, relatively high-value services. Quite a lot. So this is a service to the system operator. More talked about peak charge avoidance. So really, what this is about avoiding charges, network charges, primarily, avoiding network charges maybe on transmission and distribution. That's really important. But then there's other stuff as well, like capacity market. But arbitrage is pretty small. So arbitrage, for the moment, isn't the big thing that carries you over the line. It might be a component of your revenue stream, but not everything. But there's a spectrum of services that batteries need to provide, and I guess you need to stack them on top of one another to make it work. And without reading all of the stuff on the left-hand side, I guess the point I want to make is that it's really hard to predict where your revenues are going to come from, even in the relatively near term. And there's been a lot of people doing an awful lot more work on these markets than I have. That their predictions have been way out from what's actually happened in practice. So whether or not it's firm frequency response that has eroded enormously, whether or not it's rule changes on the capacity market, which meant your battery now needs to be almost 8 times bigger or more expensive than you thought you needed to have, and that hurt quite a lot of people, or huge amounts of competition. It's really strange. The one point I guess I wanted to make is towards the bottom here. That's really interesting, I guess, in the UK. That okay, so over here, network charges are quite important, or avoiding network charges are quite important. But yet on where the regulator is looking at trying to simplify the system, the way things work right now, maybe with triads, the way your charge, I guess, for your network access might not be fit for purpose in the future. And there may be a move towards a capacity payment, which arguably is less rewarding of flexibility. From a transmission network point of view, but then at the same time, we're seeing two distribution network operators in the UK starting to incentivize people to take load off the system at certain times with flexibility markets or congestion-based markets. So we're seeing kind of more flexibility there. So it's kind of strange. There's some really interesting kind of tensions with regards to which bit of the system is going to reward what kind of flexibility. Okay, but the main part, so basically I think the opportunity is there. It's still a kind of a nervous industry. I think everyone is sure it's going to grow, and people have got their eyes in the medium and longer term, and there's no doubt that battery capacity is going to increase. So I wanted to look at the kind of 2050, now scoot to the long term and see what batteries or energy storage might do in the long term in a fully decarbonized power system. So so this is, I think the slides will be available so that you can follow the link as well if you like. So this report was published, I think, last month, and it was a study that we did. It was a pan-European study, so we looked at kind of a whole system approach. So looked at, electricity and gas, and we looked at a variety of end uses, heat and power and transport as well, lots of different sectors. I guess the exam question was, what happens when you decarbonize the electricity sector? And also all of these other sectors as well. And I guess this particular, all the clients have a particular perspective, and this client wanted to try to balance, I think, a bit of the debate that was happening in the public sector. They said, look, we want you to push electrification as far as possible. So we want you to electrify, not on the supply side, because that needs to happen anyway, but on the demand side, let's electrify as much stuff as you can, basically heat and electricity. But then everyone is aware that particularly heat is tough, and I can show you a slide on that in a minute, that electrifying heat is really hard. And so I guess the hypothesis was, let's see how far you can go with electrification as a kind of a core plank of your decarbonization strategy, but then acknowledging that molecules and natural gas is a great way to get energy to people's houses for heating in winter. Acknowledging that could remain the case in the future, what might be the role for molecules in delivering energy to people. Of course, they would need to be zero carbon molecules, so they need to be created in a different way from now. So just kind of setting up the kind of storage issue, I guess. So we looked across Europe, but one of the hypotheses that we had is like when you have a zero carbon electricity system, so you're reliant very heavily on PV and wind, and more of the things that we saw this morning, that you're going to the kind of solution to the system that gives you security of supply for every hour of the year. Yeah, so that system is going to be driven by kind of two things that are causing you problems. One is the variability of renewables on the way in. I mean, I'm sure you all realize this. But then also you have variability of demand, in particularly heat. And then of course the third variable is that, in some countries you have gas infrastructure which is more widespread than others. So, really when you look at, the seasonality of renewable supply, the seasonality of demand, and then gas infrastructure, you can come up with a number of different kind of archetypes or different kinds of countries. And you can see how the solution is different between those countries, and that's interesting, because the same 2050 solution doesn't work everywhere. So if you look at just on the supply side here, and again, I appreciate many of you fully appreciate all of this already, but if you just take a kind of a 10-day period, I mean this is UK data from a couple of years ago, close to the middle of summer, and you've got PV, these are load factors on the y-axis, so PV and wind in orange and blue. I mean the diurnal pattern of PV is obvious, okay? But obviously wind doesn't have anything as useful a pattern, so that's a problem if you're trying to firm up these signals kind of coming into a system. You're trying to firm them up and then push them out to end users in some reasonably organized way, then that's a problem. If you then say, okay, well I'm going to have a storage system that is going to try to firm or smooth out these variables or kind of firm up the energy that's coming out of that system, obviously the signal coming out of the storage device is going to be smoother the larger that storage device is, right? If it's able to store energy for longer, it's able to deal with more of the peaks. And that's really what we're showing on this. So, if you have a storage duration in hours versus, an index of variability, so, that's how variable both of those signals are, on an annual basis on the way in. But then, after you've got 10, 15 hours of 10 or 15 hours of storage for PV, you've pretty much done all that you can in terms of firming up that energy on the way out. It gets better, but really very diminishing returns. So 10 to 15 hours is fine. You might expect that, but obviously not for wind. It stays fairly variable for a long period of time, and there's no right number, but 2 days is a lot of storage if you're going to try to balance wind. But really beyond 2 days, you have to kind of ask yourself why you're doing it and what the value of that would be, because it's diminishing returns and you're not getting your improvement, your performance is not improving. So that's kind of a problem on the supply side, because again, we're going to have an awful lot of renewable energy, kind of cold electrons on our system in the future. And then on the demand side, I'm sure many of you are familiar with this as well. I mean, this is the thing that really drives a lot of the solutions, is that, heat, so this is a peak day in Germany. I know we don't know what the peak day is going to be in Germany in 2050, but that's what we have in the model. And just for, instruction here, we have baseline electricity demand that we're predicting. But the point is, all of the reds here are different kinds of electrified heat. And then the blues are different kinds of electrified transport. And really the electrified heat is a big issue. It will double, at least triple, at least 2 to 3 times your demand at peak times. And that might not be much of a problem, because if that was sustained over long periods of time, then you could build a network and you could get some economic value out of it. But the problem is that, again, this is pretty much the same data, but is gigawatt hours per day, gigawatt hours over a year. And obviously there's very little heat demand in the summer. And so you have this kind of seasonality, and if you were to try to apply what we did previously, where we have storage duration over longer hours, I mean, it wouldn't touch this heat signal until you got to 6 months or something much longer than that. So you really need, if you want to try and solve this problem and you want to firm up the demand side, then you need a seasonal heat store. Anyway, I'm not going to go through this. This is the dispatch kind of calculation module that we used. I guess the slides will be available, except to say that on this particular piece of work, we'd seen a lot of information where people take very seriously how you dispatch the supply side, and we hadn't really seen that much work on people paying as much attention to flexibility on the demand side. And actually we feel that the two in the future need to be treated equally, that flexing demand within constraints is as important as flexing supply. And we also have a model of networks in there as well, because networks constrain you a lot if you don't make them any bigger. Anyway, so like good consultants, we have to come up with simple messages from our work. Yes, hi, 5 minutes. And the various things that we showed are building efficiency, clean electricity, and smart electrification and seasonal storage. I'm just going to focus on the two on the right here. So this is a useful graph. I mean, this is the net load over the year, organized from peak positive net load to peak negative net load. And so what that shows is that, so the net load is the load after you've put renewables on the system. And you get these kind of two triangles here, where, in this triangle over the year, you don't have enough renewable energy on the system, and you need some form of dispatchable backup. And you can have some, but you might have an awful lot of biomass. Here you have too much renewables and you have to curtail it in some way. And so really, this is a zero carbon system, and so the objective is to try to flatten this line, to try to minimize the area of these two triangles. Anyway, the point I wanted to make here is that there's some demand side response that improves the situation, makes those areas smaller. But then after battery storage, it's really interesting. You find that, particularly in Spain, you're able to economically deploy a large amount of battery storage for that reason I've just talked about, that you only need 10, 12 hours. And in a country where the optimum supply side plus the seasonality of demand is not so bad, and you have a lot of PV, then you can actually deploy quite a lot of storage, and it works very, very well. But this is, but it doesn't work everywhere. Yeah, so, sorry.
Actually, just wanted to pause, I got that wrong. That was actually 10 minutes.
10 minutes, good. That was, you frightened me there. Aha. We'll try this one. Oh yeah, good. Okay. So if we're kind of looking into what kind of comprises the storage. So if we're looking at this, so what I mean by short-term storage, I mean a lot of people in the industry would say short-term is 30 minutes or something like that. Batteries. What I mean short-term is like up to a few days. So something that where electrochemical solutions will do the job fairly well. Again, on the upper graph, we're showing the net demand here, but this time it's not organized from largest net demand to least. It's actually chronologically from June to January again. And so what you can see is that the net demand, you can imagine, you have too much renewable energy in summer. So again, this is all optimized so that you have the right amount of renewable energy on the system at lowest cost. You have too much in the summer, and so the net load is negative, and there will be curtailment unless you put it into a storage device. And we don't have enough renewable energy in the winter. So what that means for your kind of for your short-term storage device is that so what you do is that your storage device, your kind of relatively short-term, like 1 to 2 day batteries, they're basically cycling a lot. You're building up cycles on these batteries all through those kind of 9 months of the summer and the mid-season in a fairly linear manner. And that's because the net demand is going positive, negative all the time, and you're using that to inflate and deflate your batteries usefully for your system. But then you're finding these 4 or 5 months of the year where your batteries are not, they're ready to do stuff, but they just can't accumulate cycles because there isn't enough variability in the net demand. There's just not enough renewable energy coming onto the system. And so you need another kind of solution. And we offered the system hydrogen as a storage device, as a long-term storage device. So you have excess renewable energy in the summer, you can electrolyze that, put it into a hydrogen store, and then when you need electrons again, you can put that hydrogen through a hydrogen gas turbine, and generate electricity again. And so hopefully if you can kind of keep the picture from the previous slide in your minds, then again as we go through the year, the purple line is output from the hydrogen gas turbines, and you can see that they're really working on a hugely seasonal basis to make up for the loss of dispatchable supply during those winter months. And obviously they're drawing hydrogen from the store, but then obviously over the remaining months of the year, that hydrogen store is increasing as you have excess renewable energy, and you're and you're filling up that store again, ready for it to be emptied in the next winter. And yeah, we did lots of scenarios, and you know, it's never always kind of clear cut about whether or not you should use molecules or electricity. If you take the whole kind of system into account, you know, it's frustrating that you often have to equivocate a little bit, and it's not always straightforward what you need. Okay, so that was a few slides on what might be required in 2050, and so very briefly just wanted, in the last 5 minutes, to talk about some of the interesting things that kind of might happen along the way. And I guess, you know, I think I've only got 3 slides left. So the point that I wanted to make on this slide is that, you know, whether or not we're talking about transmission network investments or interconnectors or batteries or demand side response, or even if we can get people to agree to buy electric cars and then use them as mobile batteries and discharge back onto the grid, these are all sources of flexibility. And the grid's going to need an awful lot more flexibility in the future. And I guess on this slide I wanted to show that there's going to be competition and trade-offs between different kinds of flexibility. And I guess in this particular instance, you know, we can configure a system where we've got, we introduce a new load. You know, we're charging electric vehicles at the wrong time of day. It's silly. And sure, we can put cheap batteries in the long term. We can put fairly cheap batteries onto the grid to some extent and balance that out. But actually what's much better is just being smart about when we charge vehicles. But the point is, when we do that, you need less battery capacity. These are kind of utility batteries. And then, yeah, if you can manage to convince people to allow you to do vehicle to grid, then you wouldn't need any batteries at all, because there's so much capacity on the system. It's a tough gig doing vehicle to grid, but anyway, it's theoretically possible. So there's kind of competition, you know, between different flexibility assets, but even within a single asset as well. So the thing again that kind of came out of the modeling is that yeah, as you deploy more and more storage assets or any flexibility asset, the marginal value is going down while everything else is fixed, and that's because the first kind of tranche of storage capacity is doing an awful lot of work to balance these, you know, hugely variable lines and trying to get everything smoother. But then the next tranche sees that slightly smoothed line, and then it's not having to do as much work, and then the next bunch of batteries are having to do even less. And so that's a problem if you're in the battery sector, because you want these things to be cycled a lot. That's how you get your money back. Otherwise, it's just sitting there. So, you know, if you look at the average full cycles that we've seen, again, nothing's changing on these grids, then, you know, the cycles do go down. Obviously, I'm cheating with the logarithmic scale here, but yeah, you do have reducing value, and that's a problem. And, you know, in our models, we did have some economic threshold for grid storage. But, you know, the positive message that we wanted to give is that actually, if you treat everything as a system, then, you know, if you're increasing your storage capacity, the threat is that the utilization and your revenues are going to go down. But the way you combat that is by making the problem harder, by putting more renewable energy onto your system, basically. And that way you can kind of maintain your utilization rate. So there's a positive interaction between sustainably decarbonizing the grid, which we need to do anyway, and flexibility assets. And just the final 2 slides. How am I doing on time? Am I okay? Okay. And then the final 2 slides, just again, kind of looking to the future. This is some work that was done by Wood Mackenzie. I mean, I don't know if it's obvious, I'm pretty enthusiastic about this sector. But yeah, they showed, this is their work, obviously not ours, but they showed that, you know, in Australia, you know, it's increasingly accepted that, you know, batteries will be cost effective relative to peaking plants, okay? So that's, I think, been understood for a little while now. But what was really interesting, for me anyway, when I saw this, is that what they did is they took that battery capacity, integrated it with solar, and then compared it with baseload. And they found that they were potentially cost effective with baseload. So that's essentially, you know, central to, yeah, a lot of that kind of 2050 modeling that we talked about. Is it's not just peaking. You have to make, you know, you have to make green electrons. You can't just take them from CCGT. So, you know, as a kind of a stepping stone to wider deployment, I think that was really good to see. And then the last slide, some work that was done by MIT, and I was very hopeful when I saw this slide. So, you know, PV works better when it's sunny, right? And power purchase prices are really super low now. 20-year power purchase prices like less than 3 cents per kilowatt hour just for PV. You could double that when you put storage on. Still really cheap. And I guess the point is that, you know, if we're thinking about markets and we're thinking about this sector getting bigger and bigger in a sustainable way, then what they did is they just looked at the Earth and just integrated horizontally, and they said, well, okay, here's the distribution of land at each latitude. Here's where all the people are, and here's how sunny it is on average, around the Earth. And the implication is that there's an awful lot of people in places where it's pretty sunny. And I think that's a very uplifting thing, because we're very close to grid parity on PV and storage, certainly in the next 10 years in a number of markets. And as soon as this takes off, not only can we have a storage sector that is sustainable and is going to be able to grow sustainably because there's more markets, but we're also going to be able to give grid access to people who need it most as well. So good. That was it for me. Thanks very much.
You are talking about green hydrogen.
Yeah.
I understand it can be green only if you attach wind turbines,
Yes.
so electrolysis
Yes.
installations.
Yes.
But do you know of working installations of this kind? Because otherwise electrolysis is very high energy demanding.
Yes, that's right. Well, they're 70% efficient, so they're the high energy demand because there's a high energy content in the fuel that you're creating. Yeah.
I know
So,
that there
yeah.
were ideas of pilot a bus in Aberdeen.
Yeah.
They wanted to use hydrogen buses
Yeah.
with wind turbines, but it was still an idea.
Yeah.
Are there working prototypes?
Yeah, there's a number of working projects around the world, but I think, although my organisation was involved in that Aberdeen project, I'm not personally very enthusiastic about hydrogen in transport applications, but I am quite enthusiastic about hydrogen as one storage vector that needs to, but it has very precise use cases. I think that the challenge, and I'm not sure I understand how to make it work financially, is that as you can see from the previous graph, as you go towards annual storage, you're cycling your storage less until you get to the point where it's an annual store. You're inflating this and deflating this thing once a year. So how do you make enough money out of that and make it affordable? So yeah, I think, but there are quite a few trial projects, but electrolyzers are still really expensive. That means people still want to use them at almost full load, which is obviously not relevant for the future. I think in this modeling, we optimize between energy prices and the cost of electrolyzers, and I think the load factor is about 30%. So that's where we need to get to. I don't know how we get there yet, right? But you need to go from these really expensive machines to ones that come down in price, so there you can do energy arbitrage and provide some services on the system.
Okay, 1, 2, third question. Okay.
In no stage does anybody mention carbon capture and storage.
Yes.
Is it that it is hugely expensive
Yes.
compared to...
Yes, it is. Yeah. So I think I love talking about carbon capture and storage because we have to choose, I think, as a society about what kind of energy system we want in the future. That carbon capture and storage is great in theory, and it allows us to perpetuate the kind of thermally based energy system that we have currently. That most of our electrons are produced from thermal systems, and in principle, carbon capture and storage could allow us to do that. And we did, simulations. I didn't show them here, where you put quite a lot of CCS onto this, and there's loads of other papers where the system is reliant on CCS, and it's like a silver bullet. It's just you make everything so much easier. There's almost no need for flexibility and all of this interesting stuff if you have this ultimately dispatchable thermal process of gigawatts of this stuff. If you can make it work. But I think it's a very delicate and brittle situation where you would be reliant on one technology that isn't really cost effective yet. So I think I'm not against it, but it has in comparison to other technologies like nuclear, it has positive learning rates. Every time you build one, it gets more expensive than the last one, which is not the case with PV and not the case with batteries and not the case with wind. So it has some. It needs to be. We can't knock it on the head yet. We need everything we can get because the problem is huge. But yeah.
Okay, good. One final quick question or comment?
I was just wondering how you incorporated weather within the model, and kind of how much storage you need to cope with an extreme event.
Yeah. Yeah, so it is an hourly model, and we took hourly wind data from a database of historical wind data, and PV as well. So all of the model works on an hourly basis using real data as far as possible. And what we did is we chose, I think we had 15 years worth of wind data and 15 years worth of PV. Obviously, it gets better the more recent it is because the market was pretty small. We chose in both cases, the most extreme wind data that we could. So not to say we didn't do any statistical analysis to say this is a 1 in 50 year. We could do that, but we were trying to push the model to be fairly negative. So the annual data that we used was already the worst from amongst the data sets that we had. So I can't pretend it's right on that tail of that 5th percentile, but it's not the average. Yeah, it's already we're stressing the system both in terms of. Yeah, so we did it for obviously the things on the way in, which is wind and PV. We made sure that there was low wind and obviously in winter there's not a huge amount of sunlight around. But the biggest one was heating. That we made sure that it was a cold year as well, and so heating loads were high. And it turns out the heating bit is the thing that tends to drive the configuration of the system more.
Okay, so we'll reconvene at 12:30 for the last session of the day, and should we just thank the speaker again?